Hi everyone! Let's continue our salt fun with looking at basic salts. So when we have salts that are formed with weak acids, such as the ones that are listed here, and they react with strong bases, what we're going to end up having is a basic salt solution. And to understand the mechanics of that, we can look at a good example of acetic acid, which is known as our weak acid, and sodium hydroxide, which is known as our strong base. And they both react to form sodium acetate, which is our salt. And our salt is going to dissolve in water. And now when we try to understand what those ions are when they form, we can kind of understand why our solution is basic. So when we're focusing on the cation part, our sodium ions, we know that our sodium ions are a weak conjugate acid because its conjugate base, which is sodium hydroxide, is a very strong base. So our weak conjugate acid is going to react in water, or it's going to dissociate in water, and when it does, it's so weak that it's not going to be able to do anything with the water, so no reaction forms. And so our sodium ions are just spectator ions. Conversely, when we look at our acetate ions, we notice that this is a strong conjugate base to acetic acid, which is a weak acid. So this strong conjugate base is going to accept a proton from water, and when it accepts that proton from water, it's going to end up producing hydroxide ions. And the production of hydroxide ions means that our solution is going to be basic. So the driving reaction of our solution is the dissociation of our acetate ions reacting with the water to form hydroxide ions, and this is what dictates whether or not our solution is going to be basic. So with that said, we can now look at a good question that examines the pH of a basic salt. Practice 2 asks us to calculate the pH of 0.25 molarities of sodium acetate. Now keep in mind that the two things we're going to need to solve this reaction is the ionization constant of water and the ionization constant of our acid, specifically the acetic acid, which is provided here as well. So as I mentioned to you, when we're dealing with a basic salt like this that is formed from a strong base, our sodium hydroxide, and our weak acid, our acetic acid, we are going to form this basic salt. What that means is that our sodium ions are just going to be considered spectator ions, and our acetate ions are going to be the one that drives our reaction to be basic because it's a strong conjugate base that is going to hydrolyze our water and produce hydroxide ions. So to actually see what that reaction looks like, we are going to have our acetate ions, which are aqueous, react with our liquid water, and it's going to produce acetic acid and hydroxide ions. So we can create a Rice table for this reaction, and we know that based off of molar ratios, we have a 1:1 ratio of acetate to acetic acid to hydroxide ions. And then we know that the initial concentration that we started off with for our salt is 0.25. So that means that our acetate ions are going to have a concentration of 0.25. We still have not produced any acetic acid or hydroxide, so this is going to be 0 in initial concentration. When we look at the change, we know that this concentration that we started off with is going to change by a specific amount, so we're going to lose a specific amount of concentration, and in that respect, we are going to gain that same amount in acetic acid and hydroxide ions, so it's going to be plus X. And then we're going to have an equilibrium concentration of whatever initial is minus our change in concentration. So in this case, it's going to be X and X. And then this is how we can summarize our reaction. But it's important to remember that here we are dealing with a conjugate acid-base pair, specifically this being our base and this being our conjugate acid. And when this happens, we are actually seeing that there's a difference by 1 proton. What's happening here is that we are actually gaining a proton from our conjugate base is gaining a proton to become a conjugate acid, and that difference is by 1 proton, so we don't really need to use this Rice table. Okay, we can just start to plug in these values into our ionization constant for our base. So now let's actually start doing the math behind it. So if we are looking at a reaction that is going to form a basic solution, that means we are going to use a Kb, right? Which is for our acetate ions. And this is a conjugate base to our acid of HCH3OO. And we are going to use Kw and Ka of our acid to find our Kb. So let's do that. So our Kb is equal to our ionization constant of water over our ionization constant of our acid. We know that the ionization constant of water is 1 times 10 to the power of negative 14. We know that the ionization constant of our acetic acid is 1.8 times 10 to the power of negative 5. When we plug that into the calculator, we get 5.5 times 10 to the power of negative 10. We also know that we can calculate our ionization constant of our base by doing the concentration of our acetic acid minus or times the concentration of our hydroxide ions over the concentration of our acetate. And we can determine this with and without the Rice table. It's going to be x times x over 0.25 minus x, which is equal to 5.5 times 10 to the power of negative 10, which we found here. Now, it's important to note the 500 rule in this case, and that rule being that if the concentration of our base, right, over the ionization constant of our base is greater than 500, then we can say that the negative x in the denominator is negligible. So let's try that to verify if that is the case. So if we were going to look at it, we would do 0.25 over 5.5 times 10 to the power of negative 10, which equals 4.5 times 10 to the power of 8. And that is greater than 500. So then I can say, therefore, the negative x is negligible in the denominator. So let's try that now. Let's actually get rid of that negative x and let's do the math for our ionization constant of our base. So to continue, our Kb is equal to x squared over 0.25, and we know that that is equal to 5.5 times 10 to the power of negative 10. When we try to solve for x, we end up with 1.1785 times 10 to the power of negative 5 in molarity. And we know that this is also equal to our hydroxide ions, the concentration of our hydroxide ions. And so now that we know the hydroxide ion concentration, we can actually find our POH, which is the negative log of our hydroxide ion concentration. So if I plug in this concentration, I am going to end up with 4.93. But remember, this is our POH, and we were asked to find the pH. So to do that, I'm going to have to do pH equals 14 minus my POH, which is just 14 minus 4.93, which is just 9.07. So the pH of my sodium acetate salt solution is going to be 9.07, and that is in the basic range. So we confirm that this salt is in fact basic.